Hello, in this video tutorial you will learn how to write the electron configuration, how to write the orbital notation and the noble gas notation. These are three different notations in the electron configuration of atoms. First of all, you always have to follow this diagram following Aufbau principle in order to distribute the electrons in the orbitals. Know that S can only take 2 electrons, P can take up to 6, D up to 10, and F up to 14. So let's take the first question. Write the electron configuration, the orbital notation, and the noble gas notation of magnesium. So we go to our periodic table and we look for magnesium. We see that magnesium has 12 electrons. So first, the electron configuration. I'm gonna follow the arrows. 1s, 2s, 2p, 3s, etc. So 1s, 2. I have a total of 12 electrons to distribute. 2s, 2. 2p, 6. So far, I distributed 10 electrons. So I continue. 3s, 2. So like this, I distributed 12 electrons and I wrote the electron configuration of magnesium. Now, the orbital notation is the same, but we draw these orbitals. Instead of writing 1s, we draw the 1s. And we place in it 2 arrows representing 2 electrons. So this one, I draw it. Now, 2s, 2 electrons in the 2s. I'm done. Now the 2p6, the p has 3 orbitals. So when you draw it, you put 3 boxes. And in each box, there are 2 electrons because the p has a total of 6 electrons in this configuration. And then the 3s2, that's how I'm going to draw it. And this is 3s2. So first is the electron configuration. And the second example given, we call it orbital diagram or orbital notation. Now the third way is the noble gas notation. How to do the noble gas notation? In order to do the noble gas notation, we look at our periodic table and specifically at the elements of group 18. Now, magnesium has 12 electrons, so we need to select an element from the group 18 in order to select it as an abbreviated electron configuration to replace the orbitals written. So here we have helium-2, neon-10, argon-18. Argon has 18 electrons. It's more than what we are distributing. So I'm going to select the neon, and I'll write the noble gas selected in brackets. Now, neon, as I said, has 10 electrons. So 10 electrons, these are 10 electrons. So instead of 1s2, 2s2, and 2p6, I write neon, and I copy the rest. I continue with whatever orbitals remaining. So this is called a noble gas notation. Now, I'm going to take another example, do the one of nitrogen. So again, I go to the periodic table. Nitrogen has 7 electrons. So we start. Nitrogen, I'm going to start with the electron configuration of nitrogen with 7 electrons. So 1s2, 2s2, and 2p3 only because I only have 7 electrons. I know that p can take up to 6 electrons, but in this case we only need to fill in it 3. Now orbital notation would be drawing these orbitals. So here the 1s2, we draw it. That's the 1s2. The 2s2, we draw it. And the 2p, we have 3 orbitals, each one containing 1 electron. Finally, the noble gas notation. We select from the periodic table a noble gas, and then we continue with the rest. So nitrogen 7. I cannot pick up neon because neon has 10 electrons. So we choose a noble gas having less electrons than nitrogen. So here we select helium, which represents only the 1s2, and we copy the rest. I also want to mention that there are some exceptions in the electron configuration. These exceptions goes in chromium and copper. Remember, chromium has 24 electrons. If we write the electron configuration, we reach 4s2, 3d4. However, when we look at D is made up of 5 orbitals. Filling it with 4 electrons is very close to become stable. So what happens is that 1 electron of the 4s, this is the 4s, will move and fill this last orbital to have a half filled orbital. This is more stable. So chromium, we don't write the configuration as 4s2, 3d4. We change it to 4s1, 3d5. Similarly here, for copper, at the end, it is 4s2 and 3d9. But this 3d9, it was almost completely filled. These are the 9 electrons. There's only one missing spot over here. So what happens is that this electron will shift to have a completely filled d orbital, which gives more stability to the electrons of copper.